We want to finish Calculus 3 by looking at surface integrals. And here's a copy of the chart of parametric surfaces that I shared on Moodle, on paper, and in the previous video. So let's see the idea of a surface integral. If we have a parameterization where we have u's and v's, we're simply mapping points in the UV plane to points in the XY plane. And so the rectangle that we have illustrated here in the UV plane, we're going to be mapping onto this patch, which is going to be curved, probably, not necessarily, in the XY plane. We're calling that the surface that we're integrating over. So we're going to describe the area of that patch by delta S. The Riemann sum then would add up all of the function values times the areas. That gives us our three-dimensional components, function times area. So we typically write our surface integral like this, where we're doing a double integral with respect to S. And that's what we call our surface integral. So let's consider that we have a surface described parametrically with u's and v's. So a vector that's tangent in the u direction would be the vector where we take the partial of each component with respect to u. So that's what we put here. Partial of x with respect to u, partial of y with respect to u, partial of z with respect to u. So that's the tangent vector in the u direction. Likewise, a tangent vector in the v direction would contain the partials of each component with respect to v. So here, if you look at the picture, you'll notice that we have a tangent vector in the u direction. That's here. We have a tangent vector in the v direction. That's here, multiplied by some component. So again, all we're doing is saying, okay, we're adjusting the length of these tangent vectors by multiplying by delta u and delta v. So we would have the sides of the parallelogram that you see here in tan given by tu delta u and tv delta v. Well, that means the area of that parallelogram would be the magnitude of the cross product of those two vectors. Using the properties of vectors, we can write the magnitude of that cross product as the magnitude of tu cross tv times delta u times delta v outside of the magnitude bars. So here is what we will refer to delta S as. And so we can write our Riemann sum as this. Notice again that the factor magnitude tu cross tv comes out in the Riemann sum, meaning that's part of the definition. So just like in line integrals, we wrote the line integral of f ds over c in terms of t's with the factor magnitude r prime t. Well, in surface integrals, we're going to write the surface integral of f ds with the factor magnitude of TU cross TV. Now, to show you how this works, we will do a simple example of something that we know the answer to. So we're going to find the surface area of a cylinder, radius 2 and height 6, which according to our geometry formula should come out to be 24 pi. Well, we parameterize the surface, look back at your sheet, like this, and we do the tangent vector in the u direction by doing the derivative with respect to u. We do the tangent vector in the v direction by doing the derivative of each component with respect to v. We do the cross product of those, and then we do the magnitude of that. So our integral then would look like this, where all that's left is for us to describe the area of the region. Well, that's already done for us. If we're in parametrics, we want u to go from 0 to 2 pi and v to go from 0 to 6. So if we have a parameterized surface, then we evaluate our surface integral by plugging in the parameterization for our x, y, and z components, doing our factor of integration, cross product, TU, TV, and the magnitude of that, and then describing our region in whatever way we see best. Now, if our surface is not given in parametric form, which many are not, if we're given z as a function of x and y, well, look, if we use the parameterization, like I showed you in a previous section, where we have the x and y as first and second components, and then for the z component, we use the function of x and y, which we're given as z. So then, here is the derivative in the x direction, the tangent vector in the x direction. Here is the derivative in the y direction, tangent vector in the y direction, and the cross product of those would be this. When we plug that into the magnitude, we come up with this as our integration factor. So this is what our integral would look like if we have a function of x and y. Here would be our function, and our factor would contain the square root of the partial with respect to x squared, partial with respect to y squared, plus 1. And all the rest is still the same. You still have to describe the region you're integrating over. So for a function of x and y, our integrating factor is the square root of the partial of x squared plus the partial of y squared plus 1. However, if our surface can be described as a function of y and z, then look how the integration factor looks. Again, notice the similarities. This is the partial with respect to y and z. If our surface can be described as a function of x and z, then the formula for the surface integral would contain the partial of x and z. So you see the similarities. So here we're evaluating the surface integral of xz over the surface described here. Now this would be easy enough to write z as a function of x and y, so that's what we will do. However, you could write x as a function of y and z, or y as a function of x and z. They would all work fine for this surface. However, using z as 1 minus x minus y, here's the partial of x and the partial of y. So our factor then would be the square root of partial of x squared plus partial of y squared plus 1, which comes out to be the square root of 3. Now we're plugging in place of the z, a 1 minus x minus y. So here's the z from the function that we're integrating. And so this comes out to be the double integral over the region described, which we now need to figure out. So what would that region look like? Now we need to take the surface, look at the projection onto the xy plane. So here is the surface looking down from above onto the xy plane. And what we see is here is a straight line crossing the y-axis at 1 with a slope of -1. That would be y equals 1 minus x. So it would make sense then that for this region we start with dy. And so we would have dy dx with y's going from 0 to 1 minus x, and x's going 0 to 1. Now, once we get to there, how we evaluate it is immaterial, as long as we do it properly. Either evaluate it by hand or type it into your TI-89. So let's look at one more typical example. We're trying to evaluate the surface integral of y squared z squared over the surface described as the part of the cone between z equals 1 and z equals 2. We'll use Maple to get a little help in drawing the graph of that. However, do you see that we need to do the partial of z with respect to x and the partial of z with respect to y, plug those into the formula, and maybe do some simplifying. So our integration factor comes out to be root 2. So we need to replace the z with the square root of x squared plus y squared. That would be here. And then insert the square root of 2 and describe our region. So here is what the region looks like in 3 dimensions using Maple. Here's what we see when we look down the z-axis at the image of that region in the xy plane. And that's what we need to be describing. So, looks like that would best be described in polar coordinates. So, if we use dA in polar coordinates, we need again to insert the r because we're changing to polar coordinates. We change the y into r sine theta. We change the x squared plus y squared into r squared. And we look at the figure to decide what our r's and thetas need to go from and to. So our r's are going from 1 to 2, and our thetas are going all the way around the circle. Now, again, once I get that written, the mechanics of evaluating that are either do it by hand or typing it into the TI-89. However, this is what we come out with.